In 2003, the Space Shuttle Columbia broke apart during re-entry into Earth's atmosphere. The investigation that followed revealed something remarkable. Engineers had tracked a piece of foam insulation striking the wing during launch on camera. They knew the foam's speed. They knew the wing's position at the moment of impact. They knew the time elapsed from launch. From just those three numbers, they could have calculated the impact force and potentially flagged a catastrophic flaw before re-entry. They did not do the calculation in time. Kinematics is the science of describing motion, not why things move. That is dynamics, which we will get to in week 4, but how they move, where they are, how fast they are going, and how that speed is changing. It gives you the tools to take position, velocity, and acceleration, and extract every meaningful number from any moving object. Today, we build that toolkit from the ground up. Before we do anything else, we need to agree on how to set up the problem. In physics, we always describe motion relative to a reference frame, a coordinate system with an origin and defined positive directions. This choice is ours to make. Any choice works as long as we stay consistent. For one-dimensional motion, we choose a single axis, typically the x-axis, and decide which direction is positive. Once decided, everything follows from that convention. A displacement to the right might be positive, to the left, negative, or we could reverse it. The physics is the same. The numbers will differ in sign, but the conclusions will be identical. The most fundamental question in kinematics is, where is the object? The position of an object is its location relative to a chosen reference point. We call that reference point the origin. We denote position with the symbol x. Its unit is the meter. Position can be positive or negative. If we place the origin at a bus stop, a bus 1 kilometer to the east might have position x equals positive 1 kilometer, while a bus 1 kilometer to the west has x equals negative 1 kilometer. The numbers are only meaningful once we fix the origin and agree on the positive direction. Both choices are arbitrary, but once made, they must be consistent throughout the problem. Now, suppose the object moves. It starts at some initial position, x initial, and ends at some final position, x final. The displacement is defined as the change in position, delta x equals x final minus x initial. Displacement is a vector quantity. It has both a magnitude and a direction, and it can be negative. Distance is different. Distance is the total length of the path actually travelled. Distance is always positive. It does not care about direction. Here is a concrete example that makes the distinction vivid. A jogger runs 400 meters north, then turns around and runs 100 meters south. The total distance covered is 500 meters, every step she took. Her displacement, however, is only 300 meters north, that is, x final minus x initial. If she had started at the park gates and ended 300 meters north, her displacement is 300 meters north regardless of which winding path she took. This difference matters enormously in calculations. Velocity is defined in terms of displacement, not distance. When we later ask how much energy something has or how hard it hit the ground, the answer depends on displacement, not on how far it wandered along the way. How fast is the object moving and in which direction? Average velocity is the displacement divided by the time elapsed. V average equals delta x divided by delta t, where delta t is the time interval. Its units are meters per second. Because it is based on displacement, it is a vector. Direction matters. Average speed, by contrast, is total distance divided by total time. It is always positive. It is a scalar. Our jogger travelled 500 meters in, say, 4 minutes. Her average speed is 125 meters per minute, about 2 meters per second. But her average velocity depends on her displacement 300 meters north in 4 minutes, which is 75 meters per minute north. Average velocity is useful for summarizing a journey, but it hides detail. Consider a car that accelerates from 0 to 30 meters per second, then brakes back to 0. Its average velocity over the entire trip might be 10 meters per second, but at no single moment during the trip was it actually moving at 10 meters per second. The average is a useful summary, not a description of any specific instant. This is why we introduce instantaneous velocity, the velocity at a single specific moment in time. Mathematically, it is the limit of the average velocity as the time interval shrinks to 0. V equals the limit of delta x over delta tt as delta t approaches 0. If you have taken calculus, you recognize this immediately. It is the derivative of position with respect to time. V equals dx over dt. On a position versus time graph, this derivative has a clear geometric meaning. It is the slope of the tangent line to the curve at that point. If the position-time graph is a straight line, the velocity is constant. The slope is the same everywhere. If the curve is steeper, the velocity is higher. If the curve bends back down, the object is moving in the negative direction. A horizontal section of the graph means 0 slope. The object is momentarily at rest. A straight diagonal means constant velocity, uniform motion. A curve that gradually steepens means the object is speeding up. Take a moment to appreciate the power of this. Every detail of an object's motion throughout its entire journey can be encoded in one graph, and the slope at any point reveals the instantaneous velocity at that moment. The speed of an object at any instant is simply the magnitude of the instantaneous velocity, always positive, no directional information. Velocity changes. When it does, we have acceleration. Average acceleration is the change in velocity divided by the elapsed time. A average equals delta V divided by delta T. Its units are meters per second squared. Like velocity, acceleration is a vector. Instantaneous acceleration is the limit of this ratio as delta t approaches 0, the derivative of velocity with respect to time. A equals dv over dt. Because v is already the derivative of x, acceleration is the second derivative of position with respect to time. A equals d squared x over dt squared. On a velocity versus time graph, acceleration is the slope, just as velocity was the slope on a position time graph. And there is a beautiful reciprocal relationship. The area under a velocity time graph between two moments in time equals the displacement during that interval. This follows from integration, the reverse of differentiation. We will use this area interpretation repeatedly. Two subtle but important points about acceleration. First, acceleration and velocity can point in opposite directions. A car moving forward but slowing down has velocity pointing forward and acceleration pointing backward. We call this deceleration, but in physics it is simply negative acceleration. It is not a separate concept. A car moving backward and speeding up has both velocity and acceleration pointing backward, two negatives that produce a smoothly increasing speed in the reverse direction. The sign of acceleration does not tell you whether the object is speeding up or slowing down. It tells you the direction of the change in velocity. You determine whether the object speeds up or slows down by comparing the signs of velocity and acceleration. Same sign means speeding up. Opposite signs means slowing down. Second, it is possible to accelerate without changing your speed. If you change direction, your velocity vector changes, even if the magnitude stays the same. A car moving around a circular track at constant speed is constantly accelerating because its velocity direction is continuously changing. We will analyze this case in detail next week. The most powerful results in one-dimensional kinematics emerge when acceleration is constant. This is a special case, but it includes two of the most important scenarios in introductory physics: uniform acceleration under a constant applied force and free fall under gravity. Under constant acceleration, four equations completely describe all possible motion. These are sometimes called the kinematic equations, or the Suvat equations in some textbooks. Let us define the variables clearly. The initial velocity is v0. The final velocity is v. The constant acceleration is a. The displacement from the starting position is delta x, which equals x minus x0, and the elapsed time is t. Equation 1. V equals v0 plus a times t. This is just the definition of constant acceleration rearranged. If you start with velocity v0 and accelerate at rate a for time t, you end up with velocity v. On a velocity time graph, this is a straight line. Constant slope equals constant acceleration. Equation 2. X minus x0 equals v0 times t plus 1/2 a times t squared. This is the position equation. Notice the two terms. The first, v0 times t, is the displacement you would have had with no acceleration at all. The second, 1/2 a times t squared, is the extra displacement due to the acceleration. That quadratic term is why objects under constant acceleration trace parabolas in position-time graphs. Equation 3. V squared equals V naught squared plus 2 times the quantity x minus x naught. This equation is the one to reach for when time is not given and not asked for. It connects speeds directly to displacement, bypassing time entirely. For a car braking to a stop, for a ball thrown upward to find the maximum height, this equation is the quickest path. Equation 4. X minus x naught equals 1/2 times the quantity v naught plus v times t. This says the displacement equals the average of the initial and final velocities multiplied by time. This formula works because when acceleration is constant, the average velocity over any time interval is exactly the arithmetic mean of the initial and final values. A word on derivation. These 4 equations are not independent magic formulas that you memorize separately. Equation 1 is the definition of constant acceleration, rearranged. Equation 2 comes from integrating equation 1. Equation 3 comes from eliminating time between equations 1 and 2. Equation 4 comes from another combination. They are all consequences of one simple fact. Under constant acceleration, velocity changes at a uniform rate. Understanding that they are related, not independent, means you can reconstruct any one you forget, and you understand the limits of when they apply. They apply only when acceleration is truly constant throughout the interval. The moment acceleration starts varying with time, these equations no longer hold, and you must return to integration. Each of these 4 equations contains exactly 4 of the 5 variables, v0, v, a, delta, x, and t. The 5th variable is absent from each equation. That is the one you can solve for. The strategy is consistent. Identify which 3 variables are known. Identify the unknown. Pick the equation that contains all 4 and solve. Now, let us apply all of this to the most important special case, free fall. Near the Earth's surface, gravity produces a constant downward acceleration of 9.8 meters per second squared. We give this a special name g. The magnitude is g equals 9.8 meters per second squared, though for most problems we approximate it as 10. The direction is always downward, toward the center of the Earth. If we take downward as the positive direction, then A equals positive g for any freely falling object. If we take upward as positive, which is more common, then A equals negative g. Here is the result that surprised Aristotle, surprised medieval scholars, and still surprises students today. The value of g does not depend on the mass of the object. A heavy ball and a light ball released simultaneously from the same height land at the same time. In a vacuum, with no air resistance, this is exact. Galileo reportedly demonstrated this from the Leaning Tower of Pisa. More convincingly, in 1971, Apollo 15 astronaut David Scott dropped a hammer and a feather simultaneously on the surface of the Moon. With no atmosphere, they hit the ground at exactly the same moment. every student should see that video at least once. The reason is Newton's second law, which we will derive properly in week 4. For now, accept the result. Free fall acceleration is g for all objects, regardless of mass, in the absence of air resistance. We have now built the complete framework for one-dimensional kinematics. Position tells you where the object is. Displacement tells you how far it moved and in which direction, a vector. Distance tells you the total path length, a scalar that cannot be negative. Velocity is the rate of change of displacement. Instantaneous velocity is the slope of the position time graph. Speed is its magnitude, always positive. Average velocity depends only on start and end points, not the path. Acceleration is the rate of change of velocity. It is the slope of the velocity time graph. Having the same sign as velocity means speeding up. Opposite signs means slowing down. Free fall near Earth's surface has constant acceleration g, downward, independent of mass. The 4 kinematic equations apply only when acceleration is constant. Given 3 of the 5 variables, v0, va, delta, x, t, the equations let you find the other 2. Next week we extend this entire framework into 2 and 3 dimensions: projectile motion, circular motion, and relative velocity. All the same ideas now with vector components separating horizontal and vertical motion.